What we have here is light emitting diodes, LEDs, and what they are, they're a semiconductor. The diode conducts electricity only one direction, and it stops it in the other way. So if you feed it with alternating current, it will change alternating current into direct current. And if you take a diode and you add various chemical compounds to it, not only will it let electricity go only one way, but it will emit light.
It's an LED demo board. The typical way they make white light with the LEDs. Like as Jerry mentioned, you have a blue, very efficient blue emitting LED with a yellow phosphor coated device. You end up with a nice warm white emission. Or, yeah, there's white emitting LEDs, right? And there's a combination of RGB, red, green, and blue emitters inside the LED package. It's another way to make white emitting LED. Okay, well, we're looking at some examples of OLED panels. These are organic light emitting diodes.
The difference between an LED and an OLED is that with a LED, you have to use 3,5 substrates because of the fact that when you use something like silicon, which is a fourth group element, you have an indirect band gap. And so that indirect band gap means that the electron and the hole being the absence of an electron, when they come together to form the photon, they have to travel in an XY direction. So you're traveling off of a Y direction to get to the electron of the hole. And as a result, you get a release of heat as well as light. So you get more heat than you do light because of that phenomenon, or you don't get as much light because you have a lot of other phenomenon going on. So that's why they use 3,5 materials like gallium arsenide to get that light output. And you're limited to those materials to get that effect. And so when you use OLEDs, the difference is that you can use any substrate and you use organic materials, which is where the light emission process actually occurs. And as a result, that allows for a lot more flexibility in terms of the different materials or devices you can use.
Typically we form an indium tin oxide layer, which is a transparent conductive material, very commonly used in optoelectronic devices. That is sputtered onto the glass substrate. And on top of that ITO film, then we form a stack of very thin organic material coatings, anywhere from 5 nanometers thick to about 200 nanometers. Depending on your device construction, it could be anywhere from about 5 to 10 different coatings that we stack on top of each other. To make a white device, typically we form 3 emission layers, red, green, and blue. And the combined emission from those layers forms white light. After the emission layers, typically there's an electron transport layer, and the cathode acts to inject electrons into the device. It's also a reflective material, which is very important. If it's not a reflective metal, a lot of the photons will be absorbed at that interface. In the off state, it's a mirror. Basically, you can see a reflection. What you're seeing is a reflection off of the aluminum reflective cathode. The OLED materials are very efficient, and they can efficiently generate photons. We can create an OLED device that's about 30 to 40 lumens per watt efficacy without using any extraction technology. But the potential is there to get well over 100 lumens per watt if we can solve some of the problems with the light extraction.